diamonds. And so that means I focus a lot on what we call the big three. So ruby, sapphire, and emerald. And today I'm going to talk to you a little bit about sort of the geology and gemology of world emerald deposits. I know my colleague Nathan Renfro was here with you guys maybe a month or so ago. So I hope there's not too much overlap in our talks, but I want to kind of go over a few more things and sort of a little bit about geographic origin determination, which is kind of a major challenge and issue in the gemological laboratory right now. But first, we'll start with a little bit of background. So I think I probably am going to tell you guys some things you already know. I think you know what an emerald is. You're all from Colombia. I can't imagine you haven't studied emeralds to some extent. So, but you'll have to bear with me so I can kind of just go over some of the basics so we can kind of have a foundation for the rest of the talk. So, of course, emerald is the green gem variety of the mineral beryl. Beryl in and of itself on its own is colorless, right? So when it has some chromium or vanadium in there, we get the green color that we are familiar with emerald. Emerald is also hexagonal. So beryl is hexagonal, and that means emerald is a uniaxial mineral. That means if you look at it along different directions, you might see a different color. It has pronounced dichroism in many cases, from green to sort of bluish green. Some emeralds will fluoresce under ultraviolet radiation. So if you shine a UV light on an emerald, especially emeralds from Colombia, the lower the iron is, the more likely the emerald is to fluoresce sort of orangey red to red. And that's the chromium in the emerald that's giving that fluorescence. Now, I know you're all geologists, and I was a geologist as well. I was trained as a geologist, but more and more these days, I'm doing more gemology work and I'm doing more spectroscopy work. So I thought, since you are all gemologists or geologists, I might give you a little bit of background on some of the things we do. And you may or may not be very familiar with the concept of spectroscopy. And spectroscopy is going to play a part in a lot of what we do in the lab and in a lot of what we do with geographic origin determination. So very simply put, spectroscopy is the study of the interaction between matter and electromagnetic radiation. So electromagnetic radiation, of course, is a variety of different phenomena in the Earth and in the universe. So we all have light from very short wavelengths, very high energy gamma rays. And as we go up in wavelength and down in energy, we go into the X-rays, the ultraviolet rays. The visible region of the spectrum is right here from about 380 nanometers to about 780 nanometers in wavelength. And that encapsulates all the light that our eyes are sensitive to. You go into longer wavelengths, you get into infrared, and then radar, FM, and et cetera, et cetera. As gemologists, the region we're kind of more familiar with is especially this visible region, but also extending a little bit into the ultraviolet region and into the infrared region. And I'll get to a little bit of how we use this later on. This is the device we would use to get a UV Vis spectrum. And actually, we call it UV Vis spectrum, but it's really UV Vis near infrared spectroscopy. So when we're doing this, we're measuring mostly from about 200, 300 nanometers, all the way up to about 1100 nanometers. And so really it's UV Vis near infrared spectroscopy. But this instrument works, the basic concept is that you have a light source. The light source produces white light. We use either tungsten bulbs or deuterium bulbs based on what we're doing. The light is then focused through a slit to produce an intense beam of light. And that light goes through a dispersion device. And so if you've ever seen, if you remember the cover of the Pink Floyd album, Dark Side of the Moon, they've got that prism on the cover with the light coming in one side and the rainbow of light coming out the other side. And so what this prism does, and this may be a prism or a diffraction grating in a spectrometer like this, that grating or the dispersion device splits up the light into its individual components of wavelengths. And then as you move the dispersion device, you can then focus individual specific wavelengths onto your sample. And so we get to selectively choose the wavelengths that we're illuminating our sample with, and we can measure how much light gets through our sample at a specific wavelength compared to how much light gets through with the sample out of the path of the light. And so I want to go through kind of a little simple example of this, just to kind of explain the concept. What I'm showing here, this gemstone, is the mineral or the gem variety goshenite, which is the colorless variety of the mineral beryl. So this would be an almost pure end-member beryl. It would be almost essentially aluminum, beryllium, and silicon in the structure. And none of these elements on their own, none of these atoms on their own will absorb visible light very much. So what we would see is that the white light would enter the goshenite, it would bounce around the facets, and it would come back to our eyes without having been absorbed at all. You'd have white light being reflected right back to us, to our eyes. And so if we were to record a visible spectrum of the goshenite, it might look something like this. This is maybe a little bit of an oversimplification, but essentially what you would see from about 380 nanometers to 780 nanometers, you would see almost a flat line, because none of the light at any of these wavelengths is being absorbed to any significant extent. Now, we take that emerald, we take that goshenite, the barrel, the nearly pure emerald barrel, and we add some chromium to it. So we replace some of those aluminum atoms with chromium atoms, and all of a sudden we get this green color that we're familiar with emeralds. Now, all of a sudden, when white light enters the emerald, it bounces around inside the stone, and green light comes back to us through our eyes. So what's going on here? Well, essentially what's going on is that the chromium atoms that are replacing the aluminum in the structure, they actually do absorb certain wavelengths of visible light. And more specifically, the absorbance curve can be measured like this. And what we see is that we have very intense absorption around 450 nanometers, more intense absorption around 600 nanometers. So what this is doing, it's absorbing most of that violet blue light, and it's absorbing a lot of that orange and red light coming through the emerald, and it's allowing most of the green light to come back to us out of the stone. So basically it creates this transmission window in the green region of the spectrum. And so when white light enters this emerald, the chromium atoms absorb all that blue and red light, creating this transmission window where there's low absorbance in the spectrum, and all the green light comes back to us. And actually with emerald, it's not just chromium, of course. So emerald can actually be colored either by chromium or vanadium. And this is showing 3 examples of that. So on the top, there's a chromium dominant emerald with about 3,000 ppm chromium, and then only about 130 ppm vanadium. And if you're not familiar with this concept of ppm, that basically means parts per million. So 3,000 parts per million out of the emerald would have been chromium atoms, and out of every million parts of the emerald, 130 would be vanadium. Now, in the middle, we have a chromium, an emerald where the chromium is essentially equal to the vanadium in the structure. And so we have about 3,750 ppm chromium and about 3,000 ppm vanadium. And finally, on the bottom, we have a vanadium dominant emerald. This has about 800 ppm chromium and 1,800 ppm vanadium. And you can see the absorption bands are essentially in the same place with all of these spectra. And we have essentially the same transmission window occurring in all of these emeralds as well. And so the chromium and vanadium have essentially the same chromophoric effect in emeralds, which is a bit unusual in the gemological world, in the mineral world. In a lot of other minerals like corundum, for instance, chromium and vanadium have a very distinct chromophoric effects, and they produce very different colors in corundum. But for emerald, for beryl, they produce essentially the same color. And actually, we do use this a little bit in the lab for origin determination. Certain deposits seem to produce more vanadium dominant emeralds, and others produce more chromium dominant emeralds. Like the Colombian emeralds actually tend to be more dominated by vanadium. They tend to be more enriched in vanadium, and their color is more caused by vanadium than chromium. Whereas deposits like Zambia and Russia, which are hosted in kind of ultramafic bodies, they tend to be more dominated by chromium. And this kind of leads us to the next point, which is that from a geological perspective, emeralds are a little bit of a paradox. It's a little bit of a mystery how we get these 2 components together to form emeralds. And so what we need to form emerald is you need to form beryl, first of all. And to form beryl, you need to have a lot of beryllium around. But in order to form a green beryl, you need to have a lot of chromium or vanadium around as well. And so the paradox is sort of that, geochemically speaking, these 2 different components tend to be enriched in different geological environments, right? So beryllium tends to be enriched more in pegmatites, potentially in some evraporite type deposits, whereas chromium and vanadium tend to be related more to, for instance, ultramafic or mafic intrusions, such as dunites, Harzbergites, peridotite, or potentially, especially like vanadium can be enriched a lot in a lot of clays, a lot of black clays and sedimentary rocks related to that. So what do you need to form an emerald then? You need to somehow take these 2 distinct and unique geological environments and bring them together. And that's what's shown here. This is what we call a schist-hosted emerald environment. So we're going to distinguish between, in this talk, schist-hosted emeralds and metamorphic hydrothermal type emeralds. And the schist-hosted emeralds, obviously a schist is a rock that's dominantly composed of micas, right? And so these schist form when you have an ultramafic body, an intrusive ultramafic body that has been intruded by a pegmatite. And so in this case, obviously the pegmatite is bringing in this chemical component of beryllium, and the ultramafic rock surrounding it that is being intruded, that's the source of the chromium that's giving the green color to the beryl that would have been formed in the pegmatite. And that's shown again here in this schematic diagram. So what we need is this body of ultramafic or mafic rocks as the host of the source of the chromium, and then you have a pegmatite nearby. And these schist-hosted emeralds are, generally speaking, these are all magmatic related emeralds. And that means the source of the beryllium, the source of the pegmatitic fluids coming in would have been some local granitic intrusion that would have supplied these pegmatitic fluids, have been the source of the ultimate beryllium intruding into these ultramafic rocks. Now, on the other hand, we also have these hydrothermal metamorphic emeralds. So these might be the types of emeralds you're more familiar with in Colombia. These are the emeralds that form in these black shales in Colombia. And so in this case, the black shales are most likely the source of the vanadium or the chromium that's coloring the emeralds. And then cutting through these black shales are these veins. And these veins are hydrothermal fluids likely derived from some evaporite type formation related to this sedimentary package. And in this case, the hydrothermal fluids coming in most likely would have been the source of the beryllium to form the emeralds in this case. And that's kind of shown schematically here in this diagram from Giuliani et al. 2019. It's showing how, especially in these cases, these hydrothermal metamorphic emeralds, they're formed oftentimes with fluids that are related to these thrust faults or these tectonic formations in these sedimentary packages that are facilitating fluid flow through these sedimentary packages and through these black shales, bringing chemical components from like evaporite type formations in the deposits and bringing them into play with the black shales that are in these deposits as well. Now, one thing to point out, in the schist-hosted emeralds, they tend to form in these mafic, ultramafic bodies, right? And so in addition to supplying chromium for the emeralds, the mafic and ultramafic rocks also have a lot of iron sitting around. And so these schist-hosted emeralds tend to be enriched a lot in iron, whereas these hydrothermal metamorphic emeralds tend to be more lower in iron content because the rocks they're forming in don't really have those concentrations of iron in them. And now I mentioned earlier, like I was trained as a geologist, but I'm more doing gemology now. But I think as a gemologist, you have to always come to the realization that geology is really dictating everything there is about the gemstones you're looking at. And so if you really want to understand your gemstones, you have to think about geology at the end of the day. And this might be a little bit obvious, but one thing that we have to think about is that, of course, the inclusions that we see in the gemstones, we use inclusions for making almost all of our calls in the gemological laboratory. So we look at inclusions to tell if the stone has been treated. We look at the inclusions to tell the stone's geographic origin. But obviously, the geology of the geological formation conditions of the emerald are what's dictating types of inclusions we see in the gemstone. So, obviously for a schist-hosted emerald, it's unsurprising. It's not surprising at all that you look into the stone and see a bunch of mica inclusions. Mica inclusions are very common in schist-hosted emeralds because they form in a mica-rich rock. And similarly with the magmatic or metamorphic hydrothermal emeralds, especially those from Colombia, when you look at their inclusions, they tell you about the geology of the emerald formation. And so in this case, we find oftentimes emerald specimens from Colombia, these very well-formed crystals and these nodules, these rocks composed dominantly of calcite, oftentimes sprinkled with these very well-formed crystals of pyrite. And so what I'm showing in this photomicrograph on the right is an inclusion in a Colombian emerald. This is actually the main inclusion is a calcite inclusion. And actually inside the calcite inclusion is an inclusion of pyrite. And so this obviously kind of directly relates and directly reflects the geological conditions of formation for the emeralds in this deposit as well. And I think we can even take this a little bit further than that. So I'm showing here 3 photomicrographs. On the left is a photomicrograph of some fluid inclusions and a Colombian emerald. And so because these fluids were likely derived from some interaction with some evaporitic body at some point in this sedimentary package, the fluids are very saline. They're very salty. And so the fluid inclusions in Colombian emeralds especially tend to have very well-pronounced salt crystals in them. Along with this gas bubble, they have very pronounced salt crystals. Whereas in the schist-hosted emeralds, of course, the geology is going to determine the inclusions. And so what we see with schist-hosted emeralds oftentimes are inclusions of mica. Now, in a synthetic emerald, like a hydrothermal emerald, hydrothermal synthetic emerald, you might see more like phenakite, this mineral phenakite, which we don't ever really see as an inclusion in natural emeralds. And if we start to think about the thermodynamic conditions of formation for emerald, for beryl and phenakite and chrysoberyl and all these other minerals, we can look at this diagram of log activity of alumina versus the activity of silica. And we see there's this boundary between beryl and phenakite. So if you were to form a beryl with phenakite inclusions, you would necessarily have to be constrained to exist along this line in activity space for activity of silica versus alumina. And so I don't actually know exactly how they grow these synthetic emeralds, but this sort of suggests there might be some sort of a buffer in the system. So they might even be buffering the fluids that are growing these emeralds with phenakite itself in order to keep it on some specific chemical buffer. And for whatever reason, this doesn't seem to happen in nature. So when we form beryl in nature, we don't often have phenakite occurring as inclusions in it. Even in deposits like Russia, where we have, there are places where phenakite is associated, at least regionally, with the emeralds that we find in some schist-hosted deposits. We never really see them together. They seem to be occurring in their own distinct places in the deposit. And that's actually kind of shown here. So in Russia, the next slide is going to take a minute to load. It's got some very large images. But in Russia, for instance, as I mentioned, we have this deposit where we're producing emeralds. These are schist-hosted emeralds. We're also producing a lot of alexandrite from the same deposit. And even and somewhere nearby in the region, they also do produce phenakite and other beryl-rich minerals. However, we don't really ever find them in the exact same location within this deposit. And we never really find beryl inclusions in the alexandrite, and we never find alexandrite inclusions in the beryl. And so, the general region where we're finding this deposit is probably somewhere in this space when we're thinking about the activity of alumina versus silica. But we're never really existing along this line for very long. So there's no really buffer in the system keeping it there. So next, we're going to go on to a little bit of detail about geographic origin determination. I'm going to give you a little bit of a view into how we do things in the lab, kind of what we look for origin determination, and what are the properties of stones that are important for determining a gemstone's origin. Now, of course, emerald is one of the most historically important gemstones. When we think about the ancient Romans, emerald was one of the most highly valued stones in the ancient Roman world. And there's this quote from Pliny the Elder that I really like. Pliny the Elder was an ancient Roman natural historian. He lived in the 1st century AD, and he wrote this series of books about the natural history of the world. And he kind of laid out very observationally everything that was known at that time about the plant world, the animal world, and even the minerals, rock, mineral, and gemstone world. And so he actually wrote one of the books in this series about rocks, minerals, and gemstones. And he had this quote that says, "No color is more delightful in appearance, for although we enjoy looking at plants and leaves, we regard emeralds with all the more pleasure because compared with them, there's nothing that is more intensely green." And I really like this quote because he's basically saying, emerald is the greenest of all greens in the entire world. It's kind of it was the embodiment of green to the ancient Romans. And actually, if you look at this necklace, the emeralds in this necklace are not very high quality emeralds. And especially today, we wouldn't really regard those as being very high quality emeralds. This necklace, of course, is valuable because it's an ancient artifact. But if you think about the emeralds that are rolling around in the gemstone market these days, the ones in this necklace have nothing compared to them in terms of their clarity or their color and their size. The one thing I think that's going for these emeralds, and probably what would have been the most important value factor for the ancient Romans, was simply the color. These are very green stones. They had almost no transparency, but they were very green. Now, if we go forward in time about 1,600 years, we come to the Colombian emeralds. And this is part of the story of how we've come to think about origin as a value factor for gemstones. So when the first Spanish conquistadors came to South America, they discovered these emeralds. And of course, they didn't exactly discover them, because the ancient indigenous people in Colombia obviously knew about these emeralds as well. And they had their own mythology and lore and stories about the emeralds. And I think they even actually kept the Spaniards from finding the emeralds, the emerald mines, for quite a while. But once the Spaniards found the emeralds and started transporting them back to the old world, to Spain, they kind of took the whole Western world and Eastern world by storm, because nobody had seen emeralds with this quality and with this size and clarity and color before. So the stones they'd seen previously that the Romans had been mostly coming from these ancient mines in Egypt, which were producing relatively low quality emeralds. But these stones with very rich, vivid green colors and high clarity, nobody had seen anything like this before. And they were transported not only through Spain, but also through the rest of the world, into Asia especially. And a lot of the Islamic world had a very high regard for these emeralds because of their affinity for the color green. And they were some actually fantastic carvings coming out of the Mughal Empire, where they were carving verses of the Quran and other things, other religious symbols into these emeralds. And so that's kind of the next part of the story, though, is, so we had the ancient Egyptian emeralds, and then those were superseded by the Colombian emeralds, which were unlike anything the world has seen before. And it actually stayed like that for quite a while. So it wasn't until about 1834 that the next big deposit of emeralds was discovered. And so if you think about this, like if you were a gemologist 500 years ago, if somebody gave you a very high quality emerald and asked you to determine its origin, pretty straightforward, because back about 500 years ago, there was only one source for top quality emeralds, and that was Colombia. But if you go back in time about 150 years ago, somebody gives you a very high quality emerald. Now, all of a sudden, there could have been two deposits where that stone could have come from. It could have come from Colombia, or it potentially might have come from Russia. Actually, there's this kind of neat story about the Russian emerald deposit. It was discovered in 1834, supposedly by this Russian peasant who was walking home along the Tokavaya River in the Russian Urals one night, and he came upon a tree that had been toppled over in a storm. And the tree, when it was toppled over, it apparently picked up some of the ground from that its roots were contained in. And so the peasant comes over to the tree and looks in the roots and starts to see these shiny green pebbles in them. And this was the chance discovery of the emerald mine in Russia. From there, and they obviously realized these were very high value gemstones, and they started mining the stones in a big way quite a while after that. And I think actually not many people know this, and I was surprised when I first started studying the Russian deposits. The Russian emerald deposit has been one of the biggest producers of emeralds in the world for a long time. And for many periods of time, it's been one of the biggest producers, even probably late into the 19th century and the early 20th century. And then again, toward the end of the Soviet Union in about the 1980s, they might have been the biggest producer of emeralds by volume in the entire world. So all of a sudden, 150 years ago, you're a gemologist and someone hands you a very fine emerald to distinguish its geographic origin. You've got two choices. It might have been Colombia or Russia. So what would you have done? And 100 years ago, 150 years ago, you would have turned to the state-of-the-art technology at that time, and that would have been a microscope. So the state-of-the-art technology, you would have looked in your stone at the inclusions, and in most stones, you would have been able to distinguish a Colombian emerald from a Russian emerald pretty easily. So again, the Colombian emerald would have had these nice jagged three-phase inclusions with the pronounced salt crystal and the gas bubble, whereas a Russian emerald would have mostly had two-phase fluid inclusions that might have been sort of blocky in appearance, maybe sort of irregular in appearance, but there would have been a distinctive shape, morphology, and appearance to the inclusion scenes in a Russian emerald versus a Colombian emerald. Now, about 50 years ago, so let's say maybe 75 years ago, if somebody gave you a Russian or gave you an emerald and asked you to identify its origin, let's say you didn't have a microscope or you weren't very comfortable looking in a microscope, there was another technology we could have turned to separate Russian and Colombian emeralds, and that would have been UV Vis spectroscopy. And so that's kind of why I started off with that technology. This is actually a very important tool for determining origin for emeralds in the lab. And what you would have seen is that the typical Russian emerald would have had this very pronounced absorption band at about 800 nanometers. And that absorption band would have been almost completely absent maybe you would have seen a very small absorption band in a typical Colombian emerald. And what this is, this absorption band is related to iron in the beryl structure. So an emerald with a lot of iron will have a very pronounced band at 800 nanometers, and a stone with very low iron would have had no absorption band at 800 nanometers. And so all of a sudden we have this new tool for distinguishing origin between Russia and Colombia. Now, the only problem is, in modern times, obviously we have many more than just these two deposits to consider. So now if anybody gives me an emerald to identify its origin, we've got several more different deposits to be considering. And that's kind of shown here. So this is the UV Vis Spectra of all of the deposits we have to consider these days now. So on the left, we have, again, these low iron metamorphic hydrothermal stones. These are their UV Vis spectra. And we have, in Colombia, for instance, you can have either the absence of that absorption band at 800 nanometers. You might have a very small iron absorption band in some Colombian stones. But this could be confused with a lot of Afghan stones. Emeralds from Afghan are also hydrothermal metamorphic. You see some similar stones from China and from Pakistan, potentially from this deposit in Zambia, Musakashi. And so all of a sudden, the UV Vis spectrum cannot correctly identify a Colombian origin on its own. The same goes for that Russian stone. So now all of a sudden, we have deposits being discovered in Zambia, at Kafugu, in Madagascar, Ethiopia, and Brazil. And all of these emeralds have very similar UV Vis spectra as that Russian emerald. So as these number of deposits grow, we can no longer use these original tools we were using to determine geographic origin. If I see this iron absorption band in an emerald, it doesn't necessarily mean that that's a Russian emerald anymore. So we need additional tools to help us with this problem. Now, I'm just going to highlight one more thing. So when we look at this UV Vis spectrum and we look for the presence or absence of that iron absorption band, what we're really doing is separating emeralds into two geological groups. So there's the hydrothermal metamorphic emeralds with low iron absorption bands, and there's the schist-hosted emeralds with the high iron absorption bands. And by making this very broad separation, so even though we cannot identify exactly the geographic origin based on the UV Vis spectrum anymore, it does help us in a way because it helps narrow down the options we have to consider for the origin for a specific emerald. So if I see it has that intense absorption band at 800 nanometers, it could be Zambia, Madagascar, Russia, Ethiopia, or Brazil, but it's not going to be a Colombian stone. Similarly, if I see the absence of that band, it might be Colombia or Afghanistan, but it's definitely not going to be Russia or Ethiopia or Brazil. So then what do we look for after that then? So let's say we got the UV Vis spectrum. It showed us we have a hydrothermal metamorphic emerald. Now all of a sudden we're going to be considering Colombia as a possible origin. And so what we would look for in Colombia, there are certain diagnostic type inclusions, like these jagged three-phase inclusions with a pronounced salt crystal and a pronounced gas bubble. If we see very large, well-formed pyrite crystals, this is a fairly decent indication of a Colombian origin as well. There are some other deposits where you'll find pyrite inclusions, but they're not typically ever this so large and well-formed as you see in Colombian emeralds. One thing that, if you look enough into the gemological literature, one thing you'll see is this mention of parasite inclusion. So parasite is a rare earth element carbonate, fluorine carbonate mineral, and it's considered to be diagnostic for Colombian origin. So if you see a parasite inclusion in an emerald, it's basically 100% sure that that is a Colombian emerald. And finally, you might see this type of inclusion that we call gote de acete, which is this kind of turbid, roiled growth pattern that we see sometimes in Colombian emeralds. It's got this sort of cellular, granular pattern to it, this kind of columnar pattern. And we think it's basically formed when emeralds grow very quickly. And when they grow very rapidly, they may incorporate crystalline defects into the structure. And when you have high concentrations of these crystalline defects, you may perturb the light that's coming through the stone, giving this sort of turbid appearance. Now, among the hydrothermal metamorphic deposits, one of the other main deposits is going to be Afghanistan. So we don't really see many Chinese stones in the market, especially not in the international market. There might be some Chinese emeralds going around in China itself, but those stones don't really reach the international market very much. So if you see that hydrothermal metamorphic type spectrum, it's either going to be Colombia or it might potentially be an Afghan emerald. Now, there are some kind of distinct inclusions in Afghan emeralds. For instance, you might see elongate fluid inclusions like this, with kind of complex phase compositions with multiple solid phases within them, multiple gas bubbles. This is something that might be more indicative of an Afghan origin than Colombian, for instance. The only problem is some Afghan emeralds might have some jagged fluid inclusions that might look similar to what we see in Colombian emeralds. And so we do have to be very careful with this. You can't really go on microscopy alone for the most part. If you see jagged fluid inclusions, you might be inclined to say this, the emerald is Colombian, but you probably should have some additional piece of evidence in order to confirm that. And the same thing goes for the schist-hosted emerald. So let's say we got our UV Vis spectrum and it showed that intense iron absorption band, and we know it's a schist-hosted emerald. So we're thinking Russia, Zambia, Ethiopia, Brazil, maybe Madagascar. There are some certain diagnostic or at least suggestive inclusions in these types of emeralds. So for instance, Russian emeralds might have these iridescent thin film type inclusions. These are very thin fluid inclusions along the basal plane of the emerald. And when you shine a fiber optic light into the emerald from the side, from just the right angle, you might get these very bright, vivid interference patterns coming off of it. In Zambia, we sometimes see these dendritic skeletal ilmenite inclusions, again, along the basal plane of the emerald. They kind of spread out along the basal plane in these sort of skeletal patterns. Now, in Brazil, although it's not diagnostic, we oftentimes see this kind of rain-like inclusions. And when you see something like this, it's probably more likely that the stone is Brazil than any other origin. So there are some things we can look for in the microscope to help with an origin call for schist-hosted emeralds. The only problem is most of those sort of diagnostic or suggestive inclusions are not very common. So like those thin films we see in the Russian emeralds, you might see those in like 5 to 10% of the Russian emeralds, but it's not going to be very common to see that. So you cannot really rely on that as a constant indicator of origin for a Russian emerald. Now, what we might see more commonly in schist-hosted emeralds are fluid inclusions. And the problem with this, though, is that the fluid inclusions tend to look very similar between the different deposits. And so this is a photomicrograph on the left of an emerald from Zambia compared to an emerald from Ethiopia on the right. They both have these blocky fluid inclusions that mostly have basically just two phases to them, a gas and a liquid. And so for the most part, if you see these blocky fluid inclusions, it doesn't tell you anything about the origin. And that's a problem because these are the most common inclusions that we see in schist-hosted emeralds. Similarly, the mineral inclusions in schist-hosted emeralds are going to be overlapping as well. So we see a lot of mica inclusions in schist-hosted emeralds, but we see them in all kinds of schist-hosted emeralds. So seeing a mica inclusion doesn't tell you if the stone is Zambian or Russian. So what do we need to determine origin then? And I think for the most part, we need some additional piece of evidence from advanced analytical analysis. And for the most part, this is going to be trace element chemistry. So the one I'm going to talk about first is this technique we call laser ablation inductively coupled plasma mass spectrometry. You might see it called LA-ICP-MS as well. And it's actually two different instruments that work together. So there's a laser ablation system on the right, and there is a ICP-MS, an inductively coupled plasma mass spectrometer on the left. And the basic principle of this technique is that we use the laser system, the laser ablation system. We focus a laser on the girdle of a gemstone, so the outside edge of a gemstone, and we can ablate a small amount of material, or we can remove a small amount of material. And that's shown here. This is the girdle of the gemstone. These spots are about 50 microns wide, so they're about the width of a human hair. But we remove this very small amount of material, and we send this material through the ICP. So the ICP is the inductively coupled plasma. And the plasma, the material gets atomized and then ionized. So we strip apart the material into atoms and then strip those electrons from those atoms, turn them into ions. And the ions get sent through a mass spectrometer. In this case, we use a quadrupole mass spectrometer. And by filtering through the ions going through the spectrometer by mass, we can get a full analysis of the entire periodic table. And so that's kind of shown here schematically. So we have the laser ablation system on the right. We blast a small hole in the gemstone. That material that's removed gets sent through the plasma, where it's turned into atoms and then into ions. The ions go through some optics and then through a quadrupole magnet, which filters out certain ions based on mass and allows certain ions to pass through to the detector. So in this case, the quadrupole is tuned to only let atoms with mass of 57 pass through the quadrupole. And then we scan through the range of masses very rapidly on this quadrupole, and we can get the full periodic table all at once. So here's sort of an example of the output from that. This is a trace element diagram of all of our reference samples. So these are samples that we went out to the field to collect. You know, we've been to Russia, Ethiopia, Zambia, Madagascar, and Brazil to collect emeralds. And we take these emeralds, analyze their chemistry with LA-ICP-MS, and we can plot them on these diagrams to separate out these different deposits based on their origin. And so, for instance, we have very specific fields for Russia, Zambia, Ethiopia, Madagascar in this plot showing lithium versus iron. Now, we use a bunch of other different elements like lithium, magnesium, potassium, vanadium, chromium, manganese, iron, gallium, rubidium, and cesium. These are sort of the main discriminant elements that we would use to separate emeralds from these deposits. And we have very good success with this. I mean, I would say maybe 99% of the schist-hosted emeralds that come through the lab can be separated with pretty good confidence using this technique. There is one other technique we'll discuss just very briefly, and that's X-ray fluorescence. So this is a technique where we bombard the sample with high-energy X-rays, which cause characteristic X-ray emission patterns to be emitted from the stone based on its chemical profile. And so this technique of XRF is much less sensitive than ICP-MS. So we cannot measure very low concentrations of trace elements, but it is a way to separate some Colombian emeralds from other metamorphic hydrothermal deposits. And so what we do essentially is we look at the iron content of the emerald. So if we got a UV Vis spectrum that showed us we're looking at a metamorphic hydrothermal emerald, then we can send that stone to XRF to look at its iron content. If it's a very low iron emerald, it's going to be a Colombian emerald. And so we can separate that from most of these other metamorphic hydrothermal type deposits very easily by going to XRF. Still, if the results from the XRF are ambiguous, or if it turns out to not be a Colombian stone, we can then turn to laser ablation ICP-MS to get further separation between these deposits. And so what we would find is that we have, again, distinct populations, distinct regions where we would find Colombian, Chinese, Afghan, and Pakistani emeralds. And we use the same basic trace elements that we saw with the schist-hosted emeralds. In this case, we're seeing rubidium versus cesium. The Colombian emeralds fall in this very low alkali region, whereas the other emeralds tend to be more enriched in alkalis and more enriched in iron as well. And that's really kind of what I had to present to you guys today. I kind of left it a little bit short in case there's any questions, but if you have any more questions about specifically geographic origin determination, we published this entire special issue in Gems and Gemology concerning the issue of geographic origin. And so we went through there. We have articles about ruby, sapphire, emerald, and peritourmaline and alexandrite, where we go through and exactly tell you guys what we do in the lab to identify geographic origin for these different stones and what criteria we use and how we really do it. And all of these issues of Gems and Gemology are available online for no charge. You can go to gia.edu and find this issue and other issues of Gems and Gemology if there are any other questions. So with that, I mean, I guess I'll leave it up to you guys if there's any questions. I'm happy to spend some time answering anything that wasn't clear or anything that comes up to your guys' mind. Oh, I see there are a bunch of questions in the chat. So we're gonna see. Okay, so there's one question about have we done any research regarding the provenance between the Colombian emerald belts? So I guess the question is maybe, can we distinguish between Colombian emeralds from different mines within Colombia? And it's not something that we have really specifically focused on very much in the lab at GIA, because for us, we're mostly concerned with, is the stone Colombian or is it from some other country? We mostly do country-specific origin determination. There are a couple of exceptions to that. Like, for instance, we do separate between secondary Montana sapphires and Yogo sapphires from Montana, but for the most part, we mostly just consider Colombian emeralds versus everything else. So I think there's probably some emeralds from Colombia that might have, I think the mines in Colombia might have sort of general differences, but I think there's probably still quite a bit of overlap in the grand scheme of things between mines, the different mines in Colombia. So probably some emeralds from some of the mines in Colombia you could separate, but I would suspect, and again, I don't have a whole lot of data backing this up, but I would suspect that there's probably some overlap between the deposits still. And so there's another question about why do you think overlap occurs in schist-hosted emeralds? That's a really good question as well. And so I suspect it's just because of the sort of overall similarity between the geological environment in which these form. So we have a mafic, ultramafic rock being intruded by a pegmatite, and there's really only one or two ways you can do that. And so overall, they do tend to have different properties, or very similar properties. It's not like Colombia versus the other metamorphic emeralds, where in Colombia, I think the geological conditions are actually very distinct from Afghanistan and China and Musakashi. I think, you have the emeralds in Colombia forming in these black shells. And as far as I know, like even in Afghanistan, the sedimentary rocks or the environment in which they're forming is not really a black shale environment. It's still a hydrothermal metamorphic environment, but it's not the same as in Colombia. And so with the schist-hosted emeralds, I think it's just so similar between the deposits. Now, there are a few things that are different, like in the Russian deposit, you do form emeralds along with alexandrite. And actually, you see a very similar thing in Tanzania at Lake Manyara. So you do see emeralds from Lake Manyara as well as alexandrites. So there is something slightly different about the geochemical environment in those specific schist-hosted emerald deposits. Whereas like in Ethiopia and Zambia, you don't really find those alexandrites being formed in that deposit. So there are some slight variations geologically. And I think that actually is reflected a little bit in their trace element chemistry and in the inclusions. Like the Russian emeralds do actually have some distinct inclusions. They have those thin film inclusions, and sometimes they, with the Russian emeralds, they don't really have those blocky fluid inclusions that you see in Zambia. So, I think overall the geology is very similar, but there is a little bit of room for some variation, which also helps us with the trace element chemistry. That's probably why we're able to separate these stones pretty well with trace element chemistry. Now, there's another question: how long does it take to analyze the origin of an emerald? And that's a good question. So, in the lab, if we get an emerald in, so it would go through a series of steps. The first would be UV Vis spectroscopy. And actually, UV Vis spectroscopy with our current instruments is very fast. We can get a UV Vis spectrum in about 10 seconds. So that's pretty trivial. The next step would then be to send the stone either to XRF or ICP-MS. Now, an XRF analysis is going to take a few minutes, whereas the ICP is going to take a little bit longer, and that's because we have to load the stones in that laser ablation chamber like 20 to 30 at a time. And so the total analysis of those 20 to 30 stones is going to take 3 to 4 hours. And so it'll take, maybe half a day to get the ICP-MS results back, which is why we like to send a lot of the Colombian stones to XRF, because it's much faster. And then finally, you would finish all that off with observations in the microscope. And so you look at the inclusions to make sure that the observations in your microscope are consistent with what you saw from the UV Vis spectrum and from the trace element analysis. So, all told, you could get an origin report done in a day if you had everything kind of lined up and we're doing it very, very quickly and efficiently. A lot of stones, as they come in the lab, they'll spend several days in the lab just because we have such a backlog of other stones to go through as well. But if we really had to, you could do a Colombian emerald in a half day to determine its origin.
I have one.
Yeah, go ahead.
Are Colombian emeralds the only emeralds that have triphasic inclusions? That is, could these triphasic inclusions be considered as a main difference over the others?
That's a good question. And the answer is no, they are not the only ones that have the three-phase inclusions. Especially like, so the other type of hydrothermal metamorphic emeralds often have three-phase inclusions as well. Like you can see them in Afghan emeralds, even though the Afghan emeralds tend to have more kind of complex phase compositions. You do sometimes see three-phase inclusions there. There is this small deposit in Musakashi in Zambia, which is different from the main deposit in Zambia, which also produces three-phase inclusions. You can see them in Chinese emeralds sometimes as well. In addition, some schist-hosted emeralds will have more than two-phase inclusions. So I sort of simplified a little bit with those blocky two-phase inclusions in the schist-hosted emeralds. But a lot of schist-hosted emeralds will have more complex phase compositions as well. So for instance, sometimes you'll have a three-phase inclusion, which is a liquid-liquid gas inclusion. And that could be like the gas bubble has a meniscus of an additional fluid surrounding it. You'll often sometimes see solid inclusions in those blocky inclusions in the schist-hosted emeralds. Now, the main difference with schist-hosted emeralds is that they're not going to have that jagged appearance. So sort of that really jagged appearance with the the pronounced salt crystal and bubble, that's very typical for Columbia. And when you see the very big three-phase fluid inclusions that are jagged, it's a good indication of Columbia. But especially in the lab, we're very careful with our origin calls, and so we would probably try to get some additional information to confirm what we were seeing in a microscope before making an origin call. All right. Any more questions, or I'm happy to answer any more, or you can always follow up with me by email if you'd like as well. Oh, that's a good question. So is there a specific geological time when more emeralds have been produced? Actually, I'm gonna, oh man, there's a good figure from a paper that was in our special issue on gems and gemology about that. Let me see if I can pull that up real quick. Give me just 1 minute. Okay, let's see, stop sharing. All right, so there's this diagram that was published in that special issue I mentioned, the winter 2019 issue of Gems and Gemology. This is a paper written by Gaston Giuliani and Lee Grote, who are kind of two of the world's experts on the geology of emerald deposits. And they have made this wheel of time for all the emerald deposits in the world. And actually, that's a great question, because actually there's not really any one distinct period of time when emeralds were formed. We have, most of the Colombian emeralds were relatively young. Muzo's over here at about 32 million years old. Swat in Pakistan is only about 23 million years old. Malasheva in Russia is 250 million years old. And then into Brazil and East Africa, that's where you're getting about 500 million years old. And then I think, of the important economic deposits, it probably ends around 500 million years old. So we do have some older kind of emerald deposits, like San Juan is maybe the one exception to that. San Juan is about 2.6 billion years old, but most of the other deposits formed around 500 million years or 250 million years. And again, these are kind of, even though emeralds formed throughout a lot of Earth's history, they're formed with these distinct geological tectonic events, right? So 500 million years is when East and West Gondwana were colliding together in the Mozambican orogeny. Malasheva was, again, another tectonic collisional event. And so, we do have emeralds kind of forming throughout the entire period of Earth's history, but there are some sort of distinct exact periods when they were forming more commonly. So check this paper out if you have time. I'll show you the top part. So it's the paper called Geology of Corundum and Emerald Deposits in the winter 2019 issue. It's got tons of good information. I think you guys would really like that article. All right. Well, it's been great talking to you guys. And hey, if you want to, follow up, you can send me an email. There's my email address in the chat. So any other questions, feel free to send them my way. That's fine. No worries. All right. Bye, everybody.